Why calculus? What's the point of doing calculus? So yeah, imagine any kind of game. I mean, it could be a video game that if you can relate to that, or it could be a card game. But the idea is that there is some concept of challenges that you have to overcome, and you have some weapons or powers. And then for each challenge, you have to use an appropriate power or weapon. Like if you need a good defense in some situation, right, and you're trying to attack, then you may fail. Or you may need like fire versus, ice, or whatever, whatever the game is, whatever the situation is. You want to use an appropriate power or weapon to overcome that challenge. So if you kind of think in those terms, and you think about uh, the problems that we try to solve in science or math, right? But you need math to do it. You look at the various things you have learned, the concepts, the results. Suppose you think of those as powers or weapons, right? So you've learned many results in algebra, geometry, arithmetic, and you can apply those to different kinds of problems, and then you solve those problems, right? For example, if you have a problem about a projectile, like if you throw something in the air and it goes like that, right? Then you need to use some information. If you know this is a parabola, right? Then you will need to use some information about the quadratic equations that you know, and you can use that. Similarly, when there are a certain kinds of challenges, certain kind of problems where things are continuous. Do you understand continuous? Right? So I'm talking about this scenario for now, where something varies continuously. And it's not made of straight lines. So like this is not a straight line, right? This function is not a straight line. Or if you talk about the shape, you have a circle, correct? Or you have a cone, or you have like a flower vase like that. So these are not made of straight lines. It's not straightforward to find like the area or the volume of these kind of shapes. Even though you have the formulas for areas of circle or volume of cone, no one really told you where that came from, right? You were just told area of the circle is this, or volume of a cone is 1/3 pi r squared h. So where did it come from, right? Like I said, in math, you need proof. So you can't just say, oh, that volume is 1/3 pi r squared h. How? You have to prove it. So when you're dealing with situations like this, it's not enough to use the concepts we talked about earlier, the algebra, the geometry, the arithmetic, without some additional capability, right? Or if we are given a problem that, you have a container or a tank of some sort, right? And you have a tap here, and then some water is flowing into it, and the rate of flow is changing. So sometimes the water is coming fast, sometimes it's coming slow. Maybe you know how it is changing, but now you are supposed to tell how long will it take to fill up this tank, right? If it was a constant rate, it is, that's something you have done. If you know the volume and rate is some r volume units per second, right? And then you can see, okay, rate times the amount of time, if it is fixed, right, will give you that volume, and then you can figure out how much time it will take. But if the rate keeps changing, then it is hard. Then it is a difficult problem because then this doesn't work. So it's these kind of problems. Or let's take yet another example. We want to send a space vehicle from Earth to the moon, right? Earth is moving around the sun and moon is moving around the Earth at the same time. And when we have to figure out how we have to launch this spaceship, what will be its path, because as the spaceship is moving, or space vehicle is moving, the Earth and moon are also moving. They'll be out of the place where we may plan to do it, send it now. So you have to figure out a path that takes into account the motions of the Earth and the moon and the time it will take for the space vehicle to get there, and then plan a trajectory. So a lot of things are changing here, and they may be changing in different ways because Earth's speed is not constant around the sun, nor is that of the moon. It keeps changing, right? So it becomes a difficult problem. How do we handle this kind of problems? Right? That is where calculus steps in. We will also see some of these concepts can be used in some of the discrete kind of situations. We will also be able to use some of these concepts. So what is calculus doing differently that we did not do earlier? What is that? Calculus uses the concept of infinity. If you think about it, on all the previous cases, we did not deal with infinity, right? We would not deal with situations where you may be like dividing by 0, correct? Calculus uses ideas related to infinity to solve problems where we may not be dealing with straight lines. Straight lines can be in shapes or graphs or constant rate of change. Because constant rate of change is a straight line, right? A linear relationship. So calculus is using ideas related to infinity. So that's the power. That's the new power we are getting with calculus, using the idea of infinity to solve problems where we may not be dealing with straight lines, whether it is like in shapes, triangles, rectangles, etc. Or constant rate of change, meaning the rate of change itself is changing. So your graph is not a straight line when you plot the relationship. So it's allowing us, it's enabling us to solve problems that we could not solve with the previous concepts we've learned in arithmetic, algebra, and geometry, or even in trig. Trig deals with very, if you look at the sine, cosine, those functions, they're not straight lines, but they have a very regular order to it. And we are able to do some work with that even without using calculus. So let's take an example to see, just to get an intuitive idea how this works, how calculus works. Okay. What is the area of a circle? How do you know that area of a circle is pi r squared? Someone told you, right? In a book or a teacher, someone told you that area of a circle is pi r squared, but no one explained why it should be that, right? So let's try to see why it makes sense for the area to be pi r squared. Though, once you learn about some of the tools, some of the techniques, then you'll be able to prove it. Right now, I'm not going to call it a proof. I'll just say an intuitive explanation, okay? So if I have a circle, what is the circumference? Okay, let me ask, what is pi? What people observed was that no matter what kind of circle you took, you can take a small circle or a bigger circle. If they took the ratio of circumference to the diameter of a circle, any circle, it always came to be the same thing. Or at least, I mean, for them, it looked to be the same thing, pretty close. So that ratio was defined to be pi. Now it comes out to be 3.1415, you know, whatever the whole number is, the complete number is. But pi is the ratio of circumference to diameter of a circle. So that means C equals pi times D, and D is 2r, so which is 2 pi r. So the circumference is 2 pi r, and that comes just from the definition of pi. There is no derivation to it. The definition of pi is the ratio of circumference to diameter. The fact that it is a constant, it just turns out that it is a constant. It's the same thing for any circle. And we named that ratio to be pi. That gives us circumference is 2 pi r. A circle. The circle is normally just this line, just what I've drawn, and it's hollow inside. Okay, so when we're talking about the area of a circle, we're talking about the disk. Disk means it's filled up, including the internal portion. Okay, so we're trying to find the area of that. So what we'll do is we'll cut it up into sectors, right? This is like one slice of a pizza. So let's say we divide it in some number of parts, equal sized parts, and cut them out. And now I lay them like this. So suppose I had sliced it into 6 parts, then it would lay, I can lay it out like this, right? So what is this length? So this, if this is the radius, then that is the radius, right? And what is this length? See the edge of the circle, right? Is coming there, and it's also coming here, right? So how much is it on the one side? See the complete edge of the circle is the circumference, right? How much is it on one side? Half of it, because it's 2 sides, right? 3 slices are here and 3 are there. So this is circumference over 2, and this is the other circumference over 2, right? But circumference is 2 pi r. So half of this is pi r, right? Correct. So now it is, I don't know what kind of shape this is, right? So, well, what I'll do is I will keep doing this with smaller slices. I'll cut more and more slices, so each slice becomes smaller, right? And then it will look like this, right? So now I have more slices. What we did still holds, right? This is pi r, and this is r, correct? And if I keep doing this, I'll have thinner slices, but more of them. Again, this is pi r, and this is r. If I keep doing this forever, what shape is it becoming? It's becoming a rectangle. This one is r, and this one is pi r. And what is this area? Pi r times r, correct? Area. But I will never get to this, right? This means, you know, I have to cut it into infinite parts, and each part is like 0 width, correct? So this is called the limit. Right? If I keep doing it forever, it's getting closer and closer to this rectangle. Until then, it's only approximately a rectangle. So I have to use this idea of a limit, because infinite means I cannot stop. I will keep doing it forever. So I cannot find a solution by keep doing something forever, because it's never going to end. But I can make observations and I can come up with some rigorous methods to say, okay, there is a pattern. What will I end up with? What am I getting towards as I keep doing it forever? Or if there may be situations where you're not gonna get, or you're not going to be able to prove that you will get to some kind of a limiting result. So we may be able to say that there is no limit, or we can say we may not be able to prove there is a limit, or we will be able to prove that there is a limit. And that's where the power of infinity helps us. That we break something into infinite parts. We do something with each of the small parts, and then we put it back together. That's how calculus works. First, we break into infinite parts. We have something, we break it into infinite parts. And such a part is called infinitesimal. It means it's infinitely small. It's not zero, okay? It's not zero, it's bigger than zero, but it is as small as we can make it, or we want to make it. What's the smallest number bigger than zero? I'm talking about smallest number. So for example, if this is the line, right? This is zero. What's the number right after it? 0.1. What about 0.01? Is that smaller than 0.1? But then that's not the smallest because I can find 0.001, right? So we can always find a number as small as we want, right? There is no such thing as the next number on the number line. Because any number you give, I can find another number in between those, right? If you give me a 0.000001, I can find another number between 0 and that number by just taking the midpoint, for example, correct? So on the number line, there is no such thing as the next number. So if I say, okay, what's the smallest thing bigger than 0? There is no such thing, right? So I can make a number as small as I want, and that is called the infinitesimal. Just like infinity is bigger than any of these magnitudes, any number, it's not, infinity is not a number, it's just an idea. It's saying, okay, it's bigger than all of the numbers. Similarly, infinitesimal is the other side of it. It is smaller than, in terms of positive numbers, smaller than any number, but it's bigger than 0. If you break a finite sized thing into infinite parts, then the size of one part, if they're all equal sized, will be infinitesimal. Like it's not 0, right? Because if you think of it as 0, you multiply 0 with anything, then it will stay 0, right? But it kind of saying, okay, I have each thing is like 0 sized, and I have infinity of those. And then when put together, it is some finite amount, right? Like we saw for the circle. So we're breaking whatever we have, some finite sized thing, into infinite parts. Such a part is called infinitesimal. Then we do something with the parts. We could like rearrange parts like we did for the circle, or we could do something else. For example, each slice that we were cutting looked like that, right? But if it becomes infinitesimal, if it becomes really small, I could imagine that to be an isosceles triangle. This is radius, this is radius. Like this, if it is extremely thin, then it will look like flat, right? Like the surface of the earth. When we go in a field, it looks flat. But it's on a big spherical shape. In 3D, it's spherical, right? and Earth is not a perfect sphere, but if you can imagine, if you zoom in a lot, any smoothly curving shape will start looking like a straight line. Right? This is a circle, right? That's the Pythagorean theorem, right? X squared plus y squared equals r squared. So now let's start zooming in. Okay. So we'll zoom in and see this is curved everywhere, right? Let's start zooming in. See here, it looks like a perfect straight line. I'm zoomed in, right? I'm zoomed in way, you look, this is 0.005. This is 0.005. And this is 0.001 here, right? Do you see, it looks like a perfect straight line, correct? Yeah, so the curved shape, as you keep slicing and slicing and slicing, it begins to look like a straight line. Could treat it like a straight line here, right? Now it becomes an isosceles triangle. If this is B, if I could figure out what that is, right? Then what's the area for this? Because it's so small, even this, I can treat it like R. 1/2 times base times the radius. Right? So I'm able to do a simplification when I'm working with infinitesimal sizes, because the curves becomes flat lines. Right? I'm not trying to do anything here. I'm just saying we usually do something like that, where the curves become straight lines once you've broken it into infinite parts. And then we'll put it back together. In all of this, we will use the concept of limit. Right? So when we take these two things together along with the limit, so the concept of limit is underlying. If you have to work with infinities, then we have to use the concept of limit. That's a given. And when we use these breaking into infinite parts and doing something with the parts, that is called differential calculus. Right? Because here we're taking the differences, we're subtracting, we're making it into smaller parts. And when we use these two things together, this is called the integral calculus. Here we are summing, putting it together, we are integrating them together. Okay, so there are these two major parts of calculus, the differential calculus and the integral calculus, and they both use this idea of limits.